Over the past decade, venture capital poured more than $14 billion into indoor agriculture. The pitch was local, pesticide-free food grown in highly controlled, stacked environments. Between 2023 and 2025, major bankruptcies hit the sector. Industry giants that raised hundreds of millions of dollars suddenly shuttered their operations entirely. The root of this collapse lies in a biological reality. Humans perceive light based on brightness, but plants require raw photon to photosynthesize. In controlled environment agriculture, this photon demand is measured as a daily light integral, or DLI. Without the sun, generating the sheer volume of photons required for plant growth relies entirely on massive racks of specialized LEDs. This chart maps the daily light integral required by different crop types, revealing a clear divide. Shade-tolerant leafy greens like lettuce require a DLI between 15 and 25. But fruiting crops like tomatoes demand between 30 and 45. Because generating photons demands so much electricity, the indoor agriculture sector is heavily biased toward cultivating low DLI, low margin crops, just to keep the operation running. The industry miscalculated the raw cost of artificial photosynthesis. By attempting to replace the sun with electricity, vertical farms built a financial model that cannot profitably sustain itself. Every watt of electricity that powers an LED produces two outputs, photons and waste heat. Generating the massive quantities of light needed for commercial yields consumes roughly 65% of a facility's total energy budget. That massive electrical draw creates a penalty. All the waste heat emitted by the lights must be aggressively removed from the sealed room. Facilities spend another 15 to 30% of their total power running heavy HVAC systems just to prevent the plants from cooking. We can see the resulting energy disparity in this comparison chart. It shows that globally, vertical farms consume an average of 38.8 kilowatt-hours of electricity for every single kilogram of produce they yield. Traditional greenhouses, which utilize free solar photons, consumed just 5.4. Modern vertical farms relied on brute force electrical power to mandate an internal climate. Yet over a century ago, Victorian engineers solved this exact problem of large-scale climate control without a single electrical outlet. During the 19th century, the British Empire financed global expeditions to retrieve exotic plant commodities, but transporting live specimens across months-long ocean voyages resulted in massive losses. Prior to 1830, salt spray and harsh temperature swings killed roughly 19 out of every 20 plants loaded onto ships. Nathaniel Ward's portable Wardian case isolated plants within a hermetically sealed glass and wooden frame. Its passive hydrological cycle evaporated soil moisture, which condensed on the glass and dripped back down. This closed loop allowed delicate specimens to survive months without outside watering. This passive microclimate enabled the global movement of vital commodities, breaking China's monopoly on tea and shifting rubber production to Southeast Asia. It proved that an artificial environment could thrive without active mechanical intervention. As the empire successfully imported thousands of exotic plants, the demand for massive, climate-controlled environments soared. The result was the glass leviathan. Structures like the 1851 Crystal Palace covered 19 acres, wrapping massive interior volumes in crystalline grids of glass and cast iron. The architectural leap required to span these colossal spaces came from a horticulturist named Joseph Paxton. While cultivating the giant Amazonian water lily, Paxton studied the complex network of radiating, cross-linked ribs on the underside of its massive floating leaf. He observed how this natural geometry provided immense rigidity while remaining incredibly lightweight. Paxton translated this biological ribbed structure into architecture by standardizing the building around the largest single sheet of glass manufacturers could roll at the time. By using a kit of mass-produced interchangeable iron parts, he created a ridge and furrow roof that maximized light capture while minimizing light-blocking supports. By letting biology dictate the engineering, Paxton bypassed millennia of load-bearing masonry construction. He achieved the world's first modular building envelope, where a lightweight iron cage performed all structural work, while the glass merely enclosed the environment. Enclosing a massive volume of space is difficult, but regulating it is harder. Engineers had to keep tropical flora alive through freezing British winters, while preventing the glass envelope from becoming a solar oven on sunny days. To heat these structures, they utilized the thermosiphon effect. Water heated in subterranean coal boilers naturally expanded and decreased in density. This buoyant hot water naturally rose through iron pipes, circulating the building, transferred its thermal energy to the ambient air, cooled, and fell back down to the boilers, entirely via natural density differentials. To cool the buildings, they utilized the stack effect. Operable louvers at the roof's highest points released the rising hot air. This escaping heat created a pressure deficit at the base of the building, naturally drawing a constant breeze of cool outside air in through automated floor vents. Victorian engineers succeeded because their designs acted as conduits. They mediated the internal climate by intelligently guiding natural physical forces rather than fighting them with raw wattage. Rebuilding heavy Victorian glasshouses isn't a solution for modern development. Traditional architectural glass carries an immense embodied carbon footprint from its manufacturing process, often taking 20 years of energy savings just to offset its initial creation. However, the engineering DNA of Paxton's lightweight envelope continued to evolve. By the late 20th century, architects were utilizing frameless, suspended glass facades, turning the transparent skin itself into a structural element that defined buildings like the Willis-Faber headquarters. Today, material science has pushed this further with ETFE polymer cushions. Used in structures like the Eden Project, these elastic panels transmit the full solar spectrum, including vital UV light, at roughly 1% of the weight of glass. Because ETFE is a fraction of the weight of glass, the supporting steel framework can be incredibly delicate, finally reaching Paxton's goal of a transparent, nearly weightless barrier between the interior and exterior environments. These passive greenhouse mechanics have evolved into a core component of high-performance architecture, the double-skin facade. A double-skin facade consists of two distinct layers of glass, separated by an air cavity. Solar radiation naturally heats the air trapped inside this space. Utilizing the exact same stack effect engineered in the Crystal Palace, this heated air rises and vents out the top, drawing in cooler air and naturally ventilating the structure without energy-intensive fans. Buildings like Singapore's Awasha Hotel push this synthesis further by ditching hermetically sealed glass for a porous aluminum mesh covered in 21 species of living creepers and open-air sky gardens. The building uses biological evapotranspiration to actively cool the surrounding urban microclimate. The economic collapse of energy-blind vertical farms proves we cannot outmuscle the sun with electricity. Sustainable architecture must function as a breathing, symbiotic organism that collaborates with the environment rather than sealing itself off from it.